All right, so this is section 14.6. We're going to split this one into 2 days. So this is 14.6a. In both of them, we're going to be talking about what are called the directional derivatives and the gradient vector. In part A, most of the first video, actually probably the whole first video, is really going to be developing the idea of the gradient vector and directional derivatives. And the second video is really just going to be doing some problems. And really, you could probably get away with just doing video 2 if all you want to do is do the problems. But if you actually want to understand what the gradient vector and everything is, then video 1 is going to be helpful with that. Doing the actual problems, pretty simple, pretty straightforward overall. All right, so let's go ahead and talk about what the gradient is. So let's review some of the fundamentals of derivatives. So if we were to take some kind of a function, whatever this function is, and we were to say, maybe at this point right here, we'll call that x sub 0. And we're going to have some other point over here. We'll call that x sub 0 plus h. So we're just adding some distance h. The distance between those two things is h. So if x sub 0, let's use orange. If x sub 0 has a tangent line that hits it right there, then we know that f prime of x sub 0 is the slope of that tangent line. At x sub 0. Okay, there's also going to be, let's do it in red since I used red. Over here, this would be f of x sub 0. And in blue here, this one would be f of x sub 0 plus h. If we were to find the change of y over the change of x between those 2 points, so the change of y over the change of x between those 2 points, oh, that's just bad. Man, I just keep missing. Try this again. There we go. That's a little better. Close enough. Then the change of y over the change of x is a y2 minus y1 over x2 minus x1. So y2, in this case, would be f of x sub 0 plus h minus y1, which is f of x sub 0, over x sub 0 plus h minus x sub 0, which just gives you h. And that really should look familiar. We've done things very similar to this. That is the slope of the secant line between those 2 points. And then the overall general concept was, as h approaches 0, the slope of the secant, becomes or approaches the slope of the tangent. And again, none of that should be anything that you don't remember. So what we do is we define that f prime of x sub 0 to be the limit as h approaches 0 of f of x sub 0 plus h minus f of x sub 0, all divided by h. So that was the definition of a derivative in 2 dimensions. So now let's go ahead and take this to 3 dimensions. So what we have is some kind of figure Again, whatever this figure does, it's floating up here in space. Something like that. What we have is we have this line C1, maybe does something like that. It's actually sitting on the surface. So C1 is going to be it's not a line, it's a curve, but it's going to be parallel to the x-axis. So C1 is parallel to the x-axis. And it is on the surface. So then that would say, well, if we wanted to find the partial with respect to x at a specific point, then to do that, we would have to find the change of z over the change of x, because that's what the partial derivative is with respect to x. Well, that would be f of x sub 0 plus h, and then some y sub 0. Because that's, remember, now we're in 3 dimensions. So this is basically the z value minus f of x sub 0, y sub 0. So what you should notice there is that the y values are not changing, right? Because this is something which is parallel to the x-axis, so the y is staying consistent. The y is constant. The x values are changing by an h value, and then of course we divide that by h. That would be the actual change of z with respect to x. Okay, and we can do exactly the same thing. Let me see how well I can actually draw this thing again. Did something like that, like that, like that. Close enough. So then we've got some kind of a curve doing whatever it's doing. We'll call this C2, which is now parallel to the y-axis. So we'll put, I never actually labeled the point x sub 0, y sub 0. We'll put that point x sub 0, y sub 0 over here, like right there maybe. And then the point x sub 0, y sub 0 plus h. So this one, it will say is our x sub 0, y sub 0. Those are zeros. And then this point is going to be our x sub 0, y sub 0 plus h. So in this case, the y value is the only thing that's changing. The x value is staying constant. And just to kind of give you somewhat of an idea, if you were to project this down, down into the xy plane, this distance right here would be your h. So what we have is our f sub y, or our derivative with respect to y, at the point x sub 0, y sub 0. So this time we know, I'm flipping the colors here, that C2 is parallel to the y-axis. And again, it is on the surface. So the change of z with respect to y, go back to red, the change of z with respect to y is going to be f of, this comes from there, f of x sub 0, y sub 0 plus h, because the y value changed, minus the initial point, all over h. And again, you should be able to see that this one was holding x constant, whereas the one over here was holding y constant. So there you've got your partials. Okay, I hope that makes sense. I'd never labeled it. I'll I'll put our x sub 0 and then our x sub 0 plus h point here just to make sure that we have them. So that one's going to be our x sub 0, y sub 0. That one right there would be our x sub 0 plus h, y sub 0, something like that. Okay, again, I hope that makes sense. These are the partial derivatives with respect to x and y of our z values. Okay, these two were not difficult. Okay, we've done this before. We've done how does z change with respect to an x direction? How does z change with respect to a y direction? But what if delta z is in some arbitrary direction of a unit vector, which we'll call AB? So this time it may not necessarily be changing where something stays parallel to the x or y axis. It might now be in some, again, arbitrary direction of a unit vector. So once again, I'll try and draw some kind of a surface, doing whatever it's doing, floating up in space. So in this case, we're going to start off with, we'll call this point right here. That's going to be x naught, y naught, z naught. So that's our arbitrary starting point. And then we've got our second point over here, which we'll call xyz. Just some other point on the surface. So this one, let me see if I can label this. I'm trying not to do it so that I'll label it in a second. The first one is point 1 here. I'll put it up here. That's point 1. This is point 2. So now instead of having a curve that stays parallel to either the x or y axis, this is just going to be some curve that's randomly on the surface somewhere. So maybe the curve starts over here, goes through this point, comes down here, and then goes through that point, and then goes this direction. This does not appear that it would be something which is parallel to either axis, although it's really hard to tell from this. But we'll just call that curve our c value for right now. So what we do have is we have a secant line. Let's do this in orange. We have a secant line, which is going to go in between the 2 points. So we can go ahead and sketch a secant line through those 2 points. All right, so now let's see if we can follow this. I'm going to project our 2 points down into the XY plane. And this is just guessing because I have absolutely no idea where these things actually go. But we're going to project this one down to here and this one down to there. What you can see is if I project these 2 things down into the XY plane, I've got a line segment that's going to go between these. So we're going to call this P. We're going to call that one Q. I can create a vector between P and Q. And I can actually, from that vector, make it a unit vector simply by dividing by its magnitude. But what I do know is that PQ, we want that to be parallel to some unit vector. So ultimately, we want our unit vector to lie basically somewhere along PQ. So the point PQ, and we are going to use all this eventually, is the point x naught, y naught, 0, because it's projected down into the xy plane. So likewise, Q is going to be the point x, y, 0. And again, we are going to use all this. Probably should have mentioned, we're going to just define U, the unit vector, to be a vector AB. So that's going to be our definition of our unit vector. We're going to call it AB. Okay, so this is what we've got. We have that, let's go with red. the vector x minus x naught, comma, y minus y naught, that's the vector that's created between P and Q, is going to be some kind of a constant, whatever that constant is, times our vector AB. Because remember, AB is a unit vector, so it's got a unit of 1. But then we have to have some kind of a difference in between there. Well, that difference we know is H. And that's because of these points up here. Nope, sorry, didn't put the H in there. But that's because that's the difference in between the two vectors, is some kind of a difference of H, just like we did before. So by distribution, x minus x naught, y minus y naught is going to be h times A, h times B, because remember, h is just some constant. So then if I want to split this up, I know that the first component here has to equal the first component there. So really that's going to tell me that x minus x naught is HA, which means that if I want to solve that for x, I'm going to add the x naught to both sides. So I would get that x equals x naught plus HA. And then, same idea, that second component must equal that second component since the vectors have to be equal. So y minus y naught equals HB. And if I want to solve that for y, I would add y naught to both sides. I would get y equals y naught plus HB. Great. So what? Why does that matter? Well, we'll come back to it. I can say definitively that the slope of the secant, which we did create, the slope of the secant, which was kind of the orange up here, the slope of the secant is the change of z over the length from point 1 to point 2. So it's divided by the length from point 1 to point 2. Now, the reason I had to write it that way is because it's not in an x direction, it's not in a y direction, but we can find a length in between them if we can find the magnitude. So the idea is delta z, the change of z, is going to be f of xy minus f of x naught y naught divided by h times the magnitude of the unit vector AB. Of course, the magnitude of the unit vector is just 1 because it's a unit vector. So really what we get from that is f of xy minus f of x naught y naught over h. So that's really going to represent your change of z. And I say the change of z because I probably should put it's over top of the change of whatever else is going on. So we'll just say the change of, I guess, I don't know how to say this actually because there's no real way to write it. The change of the line segment. The change of the line segment, I guess. All right. But that's going to be the secant. If I wanted to find the actual slope, I would have to take the limit as h approaches 0, because we want that difference between those two points to basically become nothing. So that would be the limit of f of xy minus f of x naught y naught over h as h approaches 0, which is going to be the limit as h approaches 0 of f of x naught plus ha y naught plus hb minus, I'm going to run out of room, f of x naught y naught over h. That is the definition of a derivative in a non-specific direction, in the direction of a unit vector. The notation that we use for that is a big D, it's supposed to be in green, I don't know why it wrote in blue. A big D standing for directional derivative in the direction of a unit vector of f of x naught, y naught. Or basically, this is the way to find the derivative in any specific direction. It's not just specific to the x-axis, not just specific to the y-axis. This is a directional derivative, so a derivative or a slope in the direction of any unit vector. All right, again, there's an awful lot there as far as that's concerned, as far as the development is concerned. We're going to go through, I'm going to come back with a second video. We're going to go through a couple of what I consider to be obvious cases. Then I'm going to tell you how to do it. And then we're actually going to get into doing the problems. We're actually going to define the gradient as well, because all we have is the directional derivative. But those proofs will not take long. And then the problems are very, very short and easy.